Good day, ma'am. My name is Rolano Rebelo and my registration number is 16BLC1028. So, the name of the IEEE research paper that I've chosen is uh, Parallel Genetic Algorithm with Dispersion Correction for Hardware-Software Partitioning on Multi-Core CPU and Many-Core GPU. So, the authors are as mentioned over here. And this research paper was received on September 28, 2017 and accepted on November 14, 2017, and the date of publication is November 22nd, 2017. The date of current version is February 14th, 2018. So, as we know, in most embedded systems, a hardware platform is made up of the predominant digital components which execute software application programs. And due to this increasingly need of raising the potential quality and shortening the development time of electronic products, plus the emergence of CAD tools and hardware software co-design. The co-design has become a hot topic since the 1990s. And as we have studied in a class in hardware software co-design, the hardware software partitioning is an essential procedure because it determines which components are to be implemented on hardware and which components are to be implemented on software. So the hardware software partitioning can improve the overall performance of modern embedded systems. Over the past 2 decades, a number of works has been done for hardware software partitioning. So the target architecture of embedded systems generally consists of software components and hardware components. The software component usually uh, uh, refers to the RISC CPU, and the hardware component refers to the filled programmable gate array that's known as the FPGA, or application specification integrated circuits that are known as ASICs, ASIC, ASIC, sorry. Uh, so when the application is implemented on hardware, it is significantly faster and more power efficient, whereas the spending is very high. While when the application is implemented on software, it is power consuming and the spending is small. The speed is slow. So hardware partitioning takes care of this by ensuring that an optimal trade-off between cost, performance, and power is taken. So the application to be partitioned is given in the form of a task graph or a set of task graphs. The system to be partitioned was modeled as an undirected communication graph. Based on the model, Erato et al. Categorized two different versions of hardware-software partitioning. They are like one model can be solved in polygon time complexity, and the other can be solved in NP hard. So on algorithmic aspects of hardware-software partitioning, two categories of algorithms are utilized, namely the first is exact methods and the second one is approximate methods. Yeah, they are widely implemented with heuristic algorithms. Exact algorithm is used to obtain an exact solution for the smallest problem. The typical exact methods include dynamic programming, linear programming, and branch and bound. But when the problem size becomes large and the solution space of hardware software partitioning increases exponentially, exploring the exact solution is in reasonable time is impractical. So here is where the heuristic algorithms come into play as they become popular approximate alternatives due to their superior ability to obtain good quality solutions within the limited computing time. Now we'll go to the next slide. So in the early stage of hardware software partitioning, domain-specific heuristics, including hardware-oriented heuristic algorithm and software-oriented heuristic algorithm, are proposed. So the former starts with a complete hardware solution and iteratively moves parts of the system to the software. While the latter, that is the software-oriented heuristic algorithm, starts with the software program moving pieces to hardware. That's the reason it's called software oriented. And the hardware oriented approach is treated as a performance constraints method. The software oriented approach is treated as a time constraint method. So formally, the application of the partition is represented as an undirected graph called GVE, where V is the vertices and E are the edges. So this rotations indicate task nodes. V is equal to V1, V2 up to Vn are the task nodes. So each node includes hardware cost HV and software cost SV. E indicates a set of edges between the nodes. So the weights C, Vi, Vj, and the edges indicate the communication cost, where the two adjacent nodes are separated, implemented hardware software. So P is equal to VH, VS is called a hardware software partitioning if it satisfies VH intersection of Vs is equal to null and Vh union of Vs is equal to V. So like, that's obvious is the Vh stands for the hardware vertices. So Vh intersection of Vs is equal to null. If this is satisfied and VH is VH union VS is equal to V. So this two conditions are satisfied. So P is equal to VH comma VS is called a hardware software partitioning. So uh, accordingly, the set of P is defined as E suffix P is equal to Vi comma Vj. Whereas Vi belongs to the hardware vertices and Vj belong to the software vertices. This figure gives an example of a task graph for hardware software partitioning. Um, so partition is characterized by three metrics, namely hardware cost, H suffix P, software cost, A suffix P, and communication cost, C suffix P, this is C suffix P, sorry, which are formulated as follows. So these are the formulas, and basically this gives you the uh, relation of the total cost of partition P, which is defined as alpha HP plus beta SP plus gamma CP. So, and TP, which is the total cost of partitioning, alpha, beta, and gamma are weights which are non-negative constants, reflecting the relative importance of the three costs. Hence, two versions of partitioning problem are defined as problem P naught, which is given a graph G with the cost function SHC and the constant alpha, beta, gamma, which are greater than 0, finding a hardware software partitioning P with minimum TP, which is with minimum total cost. So problem P is defined as given a graph G with the cost function SHC and R greater than 0, finding hardware software partitioning P with SP plus CP is less than R that minimizes HP. So the software cost plus the communication cost should be less than R, and it should minimize the hardware cost. Um, so the problem P naught can be solved in polynomial time, and the problem P is NP hard as mentioned earlier. Therefore, many challenging methods for hardware software partitioning focus on problem P, as it can be solved in NP hard. Okay, so now we see the existing methods for problem P. So problem P can be directly solved or indirectly solved with different algorithms. So among the direct methods, genetic algorithm was firstly proposed. However, the solution quality and runtime of this method is not so good. So in order to address the deficiencies of above method, which is the this method. Uh, an indirect method based on 2D search was proposed to search the solution space of P. The search process of P was guided by the solution of problem P naught. To search this 2D space more precisely and efficiently, Tahi and Jahangir analyzed the search space and improved the search process. The second indirect methods try to transform problem P into a variation of standard 01 knapsack problem. So instead of a variation of standard 01 knapsack problem, View et al. Proposed Hue method. He treated problem P as a standard 01 knapsack problem without consideration of communication costs. So the temporary solution without communication cost was adjusted into a feasible solution by considering the impact of the communication cost. Experiments show that Wang's method could produce better solution quality than 1D search method. Okay, so now we see the architecture and programming of multi-core CPU and many-core GPU, which is the core topic of this research paper. So multi-core CPU and many-core GPU has become a popular parallel computing platform with low power consuming and high ratio of performance to price. Multi-core CPU and many-core GPU are available on very general PC systems. They are playing an important role in science and engineering domains. Therefore, how to use the uh, parallel power of multi-core CPU and many-core GPU on personal computers for hardware-software partitioning is an interesting topic. So this diagram over here, figure 2, shows you the difference of architecture between CPU and GPU. Data transfer between CPU and GPU is through PCIe. So this is the CPU and this is the GPU. This interface over here is the PCIe, which facilitates the data transfer between the CPU and GPU. Okay, so now I'm telling you the differences between the CPU and GPU. The difference between the architectures. The architecture of CPU is latency oriented, whereas the architecture of GPU is throughput oriented. Now, in the case of CPU, when there are complex logic judgments in application programs, the architecture of CPU shows a significant advantage of that of GPU. Whereas in GPU, when there are computing intensive parts in application programs, the architecture of the GPU shows more advantage over that of CPU. The main reason of the difference is that in CPU, logic control units and cache take up most of space, while in a single chip of GPU, arithmetic units take up most of area. At present, there are various parallel programming languages supporting multi-core CPU and many-core GPU. This paper focuses on OpenMP and Compute Unified Device Architecture, that is CUDA. So now we come to the overview of the proposed parallel genetic algorithm with dispersion correction, which is another core topic of this research paper. So as a population-based meta-heuristic standard genetic algorithm is based on the principle of natural genetics and natural selection. The core elements in the genetic search include reproduction, crossover, and mutation. So in our method that we are using, the first method, the core elements are adapted for hardware-software partitioning. We stop our algorithm when a given max number of generation is reached. In addition, if the global hardware cost was not improved in a given number of iterations, we stop the algorithm as well. If the global hardware cost is improved, we reset the no improvement count as 0. So this flowchart over here describes the algorithm of the proposed method. So the proposed genetic algorithm with dispersion correction strategy. Individual representation. So in this, for the hardware software partitioning, so X is defined as x1 x2 till n. It denotes the hardware software partitioning of problem P. So xi is equal to 1 indicates that the node vi is assigned to software, whereas where I lies between 1 to n. Hence, individual is an expression of 0, 1 to 0, 1, 0, 0, 1 iterative. The length of expression equals to number of nodes in a task graph. So this figure shows you an example of randomized individuals. So objective function, the goal of problem P is to minimize the hardware cost while satisfying constraint of software cost plus communication cost. So in this case, EHI denotes the hardware cost of VI and SI.